Hello, everybody. Good morning. Today is a real pleasure to have here Licia Verde, who kindly accepted our invitation to talk at our CosmoVerse series. Licia is currently CREA professor at ICC, that is the Instituto de Ciencias del Cosmos at the University of Barcelona. Previous to that, she was a faculty member at the University of Pennsylvania and postdoc at Rutgers and Princeton in the USA. Licia earned instead her PhD at the University of Edinburgh, and today she will present how many H are there and what do they mean. Licia, you can start, please, when you're ready.
Okay, thank you. Good morning, everybody. For some of you, uncivilized time of the day. Thank you for the invitation. And today I'll talk about some recent work done in my group, and this image is it's a representation of the cosmic distance ladder, which I'm sure you all know a lot about, given who is organizing this series of seminars. So before we start, credits what credit is due. Those who actually do the real work. A lot of what I'll be talking about is part, not all, of the thesis of PhD thesis of Samuel Bryden, who has finished and has moved to a postdoc in Edinburgh. And Samuel was supervised directly by Hector Vilmarin, who you can see there. And more recently, Niels Schonenberg has also joined the group. So you will see these names appearing over and over in the rest of the talk. So let's start with some motivation and then some background. As we know, in cosmology, measuring velocity is easy, but measuring distances is hard. And that's why we love so much the Hubble parameter, because it relates one to the other one. And one way that one can get this parameter is actually do what it says in the can, measure distances versus redshifts. And this is one of the latest picture taken from this cosmic distance ladder approach. It's harder to get directly distances to objects that are in the Hubble flow, typically cosmological supernovae at the cosmological distances. So one has got to build a ladder in there and has got to calibrate each step of the ladder. And the best calibrators has been for a very long time the Cepheid variables. But if we only just take a look at the Friedman equation, we realize that H is actually everywhere, and it's very special because we measure mostly redshift and angles, but all our theories are always written in terms of distances. So we even invented the mu little h, the units of little h, which are h naught in 100 kilometers per second per megaparsec, and then the 4h naught is a key cosmological parameters. So we can see that we have at least two cosmic speedometer. One, which is the present day expansion rate of the universe. You do what it says in the can, precession velocity versus distance. You need to build a ladder with parallaxes, Cepheids, supernovae, and then other calibrators that we'll hear about, or I'm sure you've heard about, the tip of the red giant branch, super brightness, fluctuation, masers, etc., etc. And on the other side, you have a global cosmological parameters, which is typically calibrated on early time physics after the spectacular success that was achieved with the cosmic microwave background. You can see image of Planck and the power spectra. But also we have observed the universe not just at the early time, but also at later time with the galaxy redshift surveys. So this is really a tale of two age. A priori, these two numbers do not have to coincide because they are actually not necessarily the same thing. But if they coincide, then you can say, well, it's like threading a needle from the other side of the universe, because both of them are measured with exceptional precision. And over the year, this has become increasingly, the error bar got increasingly small. And so then one can say the adopted cosmological model survive increasingly stringent tests as this agreement keeps being there. And indeed, for almost 2 decades, these two agents agree. And one can ask what happened in these 2 decades? Well, we got precision cosmology out of it. And so this was not a small feat. But then I'm sure you all know that since about 2013, then these two numbers started not to agree too well. And I reported there the numbers in kilometer per second per megaparsec of the latest result. That the TRGB is from late early 22 or late 21, and the Cepheids calibrated this in 2022. So as I'm sure you know, the tensor is here and the stakes are high. I would say that the jury is still out about what's going on. The shoes are several calibrators, but the Cepheids remains the best one. There are now TRGB and Cepheid distances measurement to the same object, and they agree with Gaia distances. So the two groups really digged out what the differences may be, and it turns out that there are differences in a special galaxy, NGC 4258. Then there is a correction on the Hubble from the supernovae. There's some correction for peculiar motion. There's some cross calibration of supernovae. You know, it's difficult measurement. It's never a simple story. So for now, what the community ended up doing, treated the TRGB as another calibrator and average out, since the measurement that is most discrepant, a smaller error bar, it pulls the numbers and so on, still end up with having attention. So let's going back to this tale of 2H, then what happens if these two numbers do not coincide? Well, you can say there are errors in the data, you can say there are errors in the analysis, or you can say there are errors in the model. And I think that we all know that every experiment has skeleton in the closet, and we can, invoking the unknown is a double-edged sword, and we can discuss about it later, but this is becoming increasingly unlikely because the data have been out for a very long time, independent group have analyzed them. In general, the teams have done a wonderful job of checking and cross-checking every step of the analysis. But what I will argue is that there are many agents, not just a couple of them, and not all measurement measure directly the current expansion rate. And this kind of plot change very quickly. So this plot is not necessarily the latest one, but it sort of gives you an idea. The different observables lands on different numbers, but we interpret this different observable giving you the same number in light of a very specific model. And it all relies not just on having the data right and the analysis right, but also believing that the model is right. And so this was the motivation. And then my question was, well, how can Galaxy Redshift Survey actually help in this, given that we are having an explosion in terms of volume and number of redshift, and more it's coming. And so just a quick recap. The key that gave this Galaxy Redshift Survey their incredible success and their motivation to actually convince the funding agency to fund them relies on the baryon acoustic oscillations. The physics, basically the physics in the early universe gives a standard ruler, which is actually a standard bubble because it's one in 3D, and it's closely related to the ruler that one has seen in the cosmic map background through the acoustic oscillation, the acoustic peaks. In the CMB, the ruler is the sound horizon recombination. For the larger scale structure, it's a radiation drag, but the two are closely related, and so sometimes one even uses the same symbol RS or RD, even though one is at sound horizon recombination and the other is really radiation. So what can you do with the BAO? One can calibrate the ruler on the early universe, either early universe physics or observation, and one end up measuring the quantity, which we're going to write down later, but for I'm sure many of you have seen this already. It's the famous dV over RD. Or one can say, well, there is a standard ruler. It's the same at all redshift because it has been imprinted there from the initial condition, but it is of an unknown length. So this is equivalent to do relative baryon acoustic oscillation. This is what I will call curly dV. And one can use the isotropy only and say, the universe is homogeneous and isotropic, but then if I see some distortion, then it means that I have some geometric effects there. And this effect is the classic Alcott-Paczynski. So let's see this a little bit more closely. So you have the clustering and you have a particular lens there, a particular ruler. And one observes it, this ruler looks smaller farther away and bigger nearby. All I measure, however, it's an angle. That's why I measure dV, which is some isotropy distance divided by RD, which is the size of the ruler. Once one measures that, then one has several options. One can say, well, I know RD because I've observed the CMB and I trust my early universe physics. So I just write the expression for this RD, plug in the number and get something. Or I can say, well, I insist I know the expression of RD, and maybe that's not the case. And so let's see what's going to happen in this plot in these cases. So what these lines are in the plane of omega mater H, what a fixed dV over RD at different redshift would look like, predicted by the number that come out from Planck in a lambda CDM. And so as the redshift change, the general direction in H omega mater plane change. Now, let's say that I insist I know the expression of RD, but in reality, the universe had a different idea and the expression was different. Then I would move along this degeneracy each time. So in other words, if I were doing that, having different redshift, measurement at different redshift will still give me the right value of omega mater. But in reality, if RD is really not the lambda CDM one, and I go and measure it. So if instead of Planck lambda CDM was something else, what Planck would have measured will be a different value for dV over RD, and therefore this line will move in this, and if you see it in this way on display. Okay, so there's more than that. Of course, there is also the fact that if one has wrong the distance versus redshift conversion, then what is an isotropic signal will appear squashed or elongated along the line of sight. This is the classics AP test. So it should be evident that since one measures only angle and redshift, and if the standard ruler length is not known, one can only constrain the expansion history E of Z, which is in a lambda CDM-like model, effectively depends on omega mater. However, if one decides to marginalize over the expansion history, then one can constrain the combination of H times RD. So the standard ruler in combination with H. And the interesting things that has enabled us to extend the cosmic distance ladder all the way from the local universe to the cosmic microwave background is that while baryon acoustic oscillation can measure absolute distances if they are calibrated on the early times and the horizon of radiation drag, then the supernovae can measure relative distances because there is a large uncertainty on the absolute magnitude of the supernovae. But the statistical power of both observables have lately become large and good enough that one can calibrate one of the other one, and so extend this cosmic distance ladder from here all the way to the early universe. So, and this is the motivation from the first slide in master. And so, if the traditional one is the direct distance ladder, one can do a direct and an inverse distance ladder. In the direct distance ladder, measures H naught, go all the way to the supernovae, now calibrate supernovae on BAO, and then go all the way to the sound horizon, or do the other way around. And this is where in lambda CDM or its simple variation, the two ladders do not seem too much. And so one can ask how much wiggle room is it there and try to do an E of Z reconstruction. And if you allow this function history to be free, and in this case, Jose Luis Bernal did it with splines, for example, then what one end up measuring in a generic reconstruction is RD time H, but it turns out that there is no much wiggle room to move away from an expansion that is described by effectively one parameter, which is omega matter. And so, well, if there is not much wiggle room in the middle, then one working hypothesis is that there's something early versus late and see what is the mismatch there. In other words, the H0 problem, if we admit that there is a problem, can be seen as an RS problem. And so this is still a relatively old plot, but it's the first one that I could find in the literature of H0 versus RS, where you had the direct measurement of H0, the constraint from a standard ruler, and this is a measurement of the sound horizon radiation drag from the CMB, but analyzed in a way that it doesn't depend on the late time expansion history of the universe. So it only really depends on the early time physics and not the late time physics. And this is the plot done by the EBOS collaboration some 5 years later, and you can match the two to see how much things have changed since, and they are really consistent even though the errors are sharp. So let's keep in mind that you can get RS in at least 2 ways. From CMB observation from a given cosmological model, or using the equation above, a model for the early universe and a constraint on the baryon density. For example, theory of BBN and light element abundances. Then baryon acoustic oscillation, even the relative one, give the matter density, and then you have all the ingredient to put it in there and obtain some constraint on RS. So one can ask, what is the problem? Is it in any specific data set? And for a while, people said, well, maybe the problem is with the Planck data. But it turned out that H0 early did not budge, even if one took out the Planck completely. And since 2019, it turns out that one can take away CMB data completely. One need to rely on BBN and early element abundances, but the early time RS and therefore the early time H0 do not budge. Before then, this is well, there is another reference. This is Schoenberg. Yes, this is reference. Schoenberg et al. 2019. People had to use CMB, some sort of CMB data. And so at that time, in order to obtain that constraint, even for a free number of expected neutrinos species, the galaxy BAO had to be combined with the Lyman alpha BAO to break this degeneracy. And there was some talk that maybe the Lyman alpha BAO were not fully consistent. And then one could say, well, but then instead use the supernovae and so on and so forth. Well, it turns out that today, with better data and better interpretation of the BBN, that's where the constraints are, and there is good agreement between the Lyman alpha BAO and the large scale structure BAO from the new data. And so that yellow that I put by hand on top of the previous plot come from this kind of plot, the same author, but a few years later, the axis got switched. But different, you can read all the list of different data set combination and you still find consistency and a nice constraints in there. So the early universe is stubbornly in the 68 kilometers per second per megaparsec camp. So where is the problem? If not in the data, then maybe in the model. And the last time Countryman decided to do something like that did not end up too well. So I'm give you my very partial personal view, and I'm happy to discuss. So one approach is what Niels and collaborator took about a year and a half ago or so, which going through a whole suite of models, they call it the H-Naught Olympics, and then see which model were better fit to the available data, and gave them even medals. And the upshot of this is that pre-recombination solution seems to be favored. So what are pre-recombination solutions? Pre-recombination solutions are rarely time solution, and we have to admit that Lloyd Knox and collaborators say that back in 2019 already. So you have to modify the model right where you most like it, which is you tinker with the sound horizon and radiation drag. You need to decrease the sound horizon by 7%, but without breaking havoc on the CMB damping tail and everything else. So this is a tall order. And it turns out that most of the wiggle room is in the decade of expansion of the universe just before recombination. And that's where the early dark energy model started exploding, because they do exactly that. This reminds me a little bit of fine-tuning, but but fine-tuning has got two sides. It could be fine-tuning, or it could be that your model is so predictive and so rigid that maybe it's the right one. So we'll see. So the upshot of this, that is early time pre-recombination solution seems to be preferred. Late time post-recombination solution do not appear to be viable, that read. They are heavily disfavored by the data. It doesn't mean that there is no wiggle room to change the late time expansion history, but there is not enough wiggle room to actually solve a 7% discrepancy. So my take of this from this point goes as follows. Cosmology tends to rely heavily on models, both for the signal and the noise, but we know that all models are wrong. I mean, some are useful, but all models are wrong. So how do you test the model, and can you do without? And so this brings back the following. There are two philosophies to constrain cosmology from the larger scale structure. And what we all learn and get taught in cosmology classes is the following one, which is I call a compression. So you extract the baryon acoustic oscillation, you extract the Redshift space distortion. If you don't know what it is, I'm going to say it in a few minutes what it is. So the baryon acoustic oscillation, we already talked about that. This is this standard ruler, and the signal is the angular location of this oscillation, not their amplitude. One measures the expansion history, not its normalization, because one measures angles and not distances. And early time physics information or data gives the length of the ruler. This is effectively data compression. And the Redshift space distortion compression is basically picking up a physical signature or a feature of squashing along the line of sight due to peculiar velocity of objects that are turning around, deviating from the Hubble flow before they collapse under gravity. And so peculiar velocity asserts by gravitational pull of inhomogeneities, and therefore one measure growth of structure, and in a Landau-CDM type model, one interpret this feature, which is this squashing, as the combination of parameter f sigma 8, where f is the linear growth rate, d log delta d log a. So this is effectively a data compression. So that's one way to analyze a large scale. But the other way is to do like for the CMB. You pick a model and fit the whole anisotropic power spectrum. For the CMB, it's just 2D, so it's not anisotropic. And approach one is say to be more model independent, because one constrain physical quantity, not parameter of the model. And then this feature or physical quantity then are interpreted within a model. And that's where the constraint on the parameter comes in. Approach number two is more computationally expensive and obviously more model dependent, but they give much better constraints. So the question we were asking with Samuel Bryden and Hector Gilmarin is, where is and what exactly is this extra information that one methodology picks up and the other one doesn't? And ideally, can one extend approach 1 to match the statistical power of approach 2? And if we really, really, really want to be good, we ask, can we conserve the speed up of 1 versus 2 and conserve the model independence? So this is a tall order, but let's see. So this is a visualization of the difference between what I call approach 1 and approach 2. Again, little omega called dark matter versus H. These are the constraints in gray from ratio space distortion alone. In orange, from the standard compression, DAO plus RSD fit. And in blue, this approach 2, which is pick a model and just analyze it the way the CMB does. And you can see that the blue has much smaller constraints. And then you can ask, well, you know, what's the star? So the star is a model that Samuel picked by hand and say, look, the red model, it's a good fit in approach 1, perfectly viable, but not in approach 2. So where's the difference? And then go and actually look how the blue and the red model fit the data and how they can be interpreted, how the compressed variable are interpreted in terms of fitting of the data and the model. So on the left side of the plot, you see how the two models fare in terms of the measurement from the data and the theory model. And you see that they are both quite good fit for all the compressed variables. But when you go and look actually at the data, most of the difference is here on very large scale. And that's why the red model, it's a worse fit than the blue one when you do the full fit. It's because the compressed variable don't look at the large scale, and that's why. Okay, great. So it turns out that the difference in information content between approach 1 and 2 is mostly the behavior of the matter transfer function turnaround. That is the detail of this function history around matter radiation equality, but to a smaller extent, the amplitude of the BAO, although we have to be careful because the amplitude of the BAO is affected by nonlinearity, possibly affected by biases. So, but luckily, it's a much smaller extent, the information content of that. And so the thing is, okay, well, just let's model this large scale shape and compress it all in one parameter and take this parameter to be the slope of that at some pivot point. And so this is developed in these two papers, and the extra parameter, we call it the shape fit parameter, or M, which is the largest scale slope of the power spectrum. And so this is a trip back down memory lane, although not quite. If you remember in introductory cosmology course, you end up plotting a transfer function. This comes basically from BBKS. It doesn't even have the baryon acoustic oscillation. This is like 90s, before the Eisenstein and new paper of baryonic feature in the matter transfer function. And so what we learn from there is that, you remember, you plot the matter transfer function where you have K equality on one axis and the transfer function on the other axis. And there is a slope there. This is my not very successful attempt to do animations. So since this is taken from BBKS, there's no BAO wiggle and there is no baryonic suppression in this plot, but it makes it much more transparent. And then if you change K equality, you're going to move the blue line left and right, because the transfer function is always 1 on the very large scales by definition. And then if you move it, that line, that slope at the same point in that curve has moved. But with respect to the previous slope, the slope has also changed if you keep measuring it in the same place. So this is basically the shape parameter, shape fit parameter M. So let's recap. Large scale structure then give you more than one H. BAO give AP, minimal, uncalibrated expansion history, as in a lambda CDM omega matter, or an early universe calibrated H naught. So you can use dV over RD and use the expression for RD either using CMB or dBn. And so you need the omega baryon from dBn, and then you get a combination of omega matter H. The relative VAO curly dV make no assumption about RD, except that one exists, and therefore in a lambda CDM framework gives a constraint on omega matter at late time. And the AP distortion with respect to the line of sight gives omega matter. And growth of structure also give a constraint on omega matter. But the large scale shape of the large scale structure power spectrum can also be used. And this has information about matter radiation equality, which in lambda CDM, it's related to omega matter H square. Of course, one needs to assume a BDN prior on baryonic baryon abundance, and for at least for current data, one needs to assume a low power spectrum with a given NS, otherwise there's not enough statistical power to disentangle the two. So more generically, I've compressed the data in a model agnostic way by extracting physical feature. If feature correspond to a specific epoch or physical process or ingredient, and a good model must get this right. So I can interpret the feature within a model and get constraints on the model parameter from that specific feature. And I would argue that a good cosmological model should get all the features and aspects right, not just one at a time. So if a model is incorrect in some aspect feature, it fails in a specific, in modeling a specific feature of aspect, then the corresponding value of the model parameter will be nonsense. It will be biased. Let's put it this way. And so if one keep on going in this train of thought, then one may know which aspect of the universe are not captured correctly by the model one has chosen. That is, one may know where the model failed and therefore where the model need to be tweaked. So let's try to play this game. We'll still project this feature into a lambda CDM model parameters, but now check for inconsistencies. And so in order to do that, let me walk you through what the expectation should be and then what the data tell you. So we write down the expression for RD. In a lambda CDM, we know how dV over RD depends on omega matter and H as a function of redshift. This is all Planck calibrated. We know how the Ka equality is related to the M-shaped fit parameter, and we know how K equality is related to omega matter H. And so we can, these are different, the different redshift reported here, and I chose this redshift because then when we go and look at the data, these are the effective redshift of the samples that the data are gonna have. And so this, we've seen it before, and these are 1% error on dV over RD. This is the constraint obtained from constant K equality, and this is an error on M of 7%. And this is the Planck omega matter, and this is a 5% error on omega matter. So since this line are all Planck calibrated, they all cross at this point as they should, because this is just theory so far. And let's put some observations on top taken from the literature. So this is the first shape fit paper before we realized that we could play this game with those data. This is also part of some brighter thesis. And these are the published dV over RD constraint from BOSS and eBOSS. There's more data, but then it will make the plot a little bit too busy. So I'm just showing you this for now. And this omega matter constraints, I've taken it from Pantheon Plus. So far so good. Then I dig a little bit more in the literature and I go and look at the Bernal paper that says I reconstruct the expansion history with splines and I measure RD time H, and then if I put it in this plot, then I get this. So also here, there's some consistency. But given that the BOSS and eBOSS data became available recently, then why not to play this game directly? And so this is what happened if you actually do MCMC from the eBOSS data. And the line here are still the theory line that you got from the previous plot, but now with the contour resulting from the MCMC. These are from the LRG galaxies, and these are LRG plus QSO plus Lyman alpha. So for Lyman alpha, one can't do this because we have only the BAO, but from LRG and QSO, yes, one can do that. So there seems to be agreement within a lambda CDM of all these constraints, and agreement with the theory prediction. So then one can get several different H. One can get H, which I call M, which is based on the interpretation of the largest scale shape of the power spectrum, or that is equality scale. And the HRD, which is an H based on the RD expression where the omega baryon constraint come from VVN. And then one can combine the two since they are in agreement and obtain HM, RD. And you can see around which value they are clustered, but I'm going to visualize it later actually in a whisker plot. So this approach is actually similar and complementary to Trista Smith and collaborators' work, where they still pick a model and then do the approach, say, what I call number 2, say, but in that model, they do marginalize over RD and say, then therefore, all the information I get, it's independent on RD because I marginalize over it. And therefore, they publish H constraints that are independent on the Sander-Eisen radiation drag. What is done here is extract the physical signal and then interpret it in the context of the strictly necessary aspects of a model. And so using consistency between all these different features then reduces the freedom that a model may need to match all these different physical signatures. So one can ask me then, what are you actually measuring? I mean, are you using the turnaround of the power spectrum as a standard ruler, or are you doing something slightly different? Because we are measuring a slope of the large scale shape of the power spectrum, but is that like doing a standard ruler using K equality as the standard ruler? So this is a test on a mock EBOS LRG, and it's that Samuel did. So in one case, the mock has BAO and is analyzed also with the shape. That's the blue solid one. The green solid one is a mock with BAO that is analyzed with a template that is fixed where M is not a parameter, so it's kept fixed. This is the standard approach before introducing the extra constraint coming from the large scale shape. And the dashed line, it's a mock where there are no BAOs. And therefore, if one can measure any BAO parameter, which is there is a standard ruler, and then I'm doing the Alkop-Paczynski and the dependence of the standard ruler on the distance, then this must be the equality scale because it's the only one that I have left. I would not be able to do that if I just had a power. And it turns out that the constraint one get on this parameter from not having the BAO and only having, therefore, the K equality are much weaker than the constraint one get using M. Basically because these come from much larger scales where the cosmic variance is larger. It's the same physical process, but the signature one is looking at is slightly different. So this has actually been attempted on data very recently by Barkalus and collaborators on the quasar sample because it's big enough to actually see this very large scale, and it's interesting to see what they get there. what is, I think, also interesting to know is that there are, in the omega matter age plane, these two approaches, M and using the quality scale as a standard ruler, gets different age dependencies. So of course there's going to be a covariance between the two, and that's a question to discuss whether you can do a joint analysis eventually with survey that have a large enough volume. But it's interesting to note that the Ka quality as a standard ruler depends on omega matter age, while M depends on omega matter age square. Okay, so let's recap. Say that there is a change around the recombination and RS is different. What would happen to those dashed lines? Can you guess? I let you think a few seconds and then I give you the result. I show you the result. So if there are changes in recombination and RS is actually different, and I actually put that in my model because I know it's different, then those lines will all coherently move left and right. Remember, these lines are dV over RD for different redshifts. Next question for you. What happens if I change the expansion history at late time? That is, lambda is not constant, there is a W equation of state of dark energy that is not fixed to -1, or something like this, or omega matter depends on time. Try to guess, and then I give you the answer. These lines will move up and down because the omega matter you interpret is not the actual omega matter out there. It's an effective omega matter that fits the expansion history. And what happens if there is something around matter radiation equality, say extra radiation or a different H of Z, a redshift around 3000, what do you think will happen? I'll let you think. Then this line will move in that way. And so say that you want all these constraints from actual real data to hit here. What would you need to do? Well, you can say, well, maybe RS is different and I'm going to move all this line down that way. I can't do too much about omega matter, or if I move omega matter, I have to be careful because they need to cross in the right way. But then it turns out that depending on which omega matter constraint you have, right now the constraint on omega matter, it's still has got enough freedom that you can just change RD and do nothing to equality and still hit this sort of target space. But if your omega matter, instead of being the one that comes from the AO expansion history, it's the one given to you by the supernovae expansion history, which is this gray one, then you can't hit that point here unless you change coherently both the sound horizon radiation drag and matter radiation equality. So the physics you have to invoke needs to change these two physical epochs coherently at the same time. So since my time is almost up, I'm not going to say too much about this, but I'm going to say that we didn't discuss redshift space distortion too much, but redshift space distortion maybe say something about sigma 8, and we know that there is another brewing issue with with sigma 8. And within a model, all these quantities end up being related. In a lambda CDM model, we can write down how F sigma 8 at different redshift is related to omega matter H, but now you also need the amplitude of the primordial fluctuation, so AS from the CMB. And so you have one quantity which is measured, and therefore it can be, with some error bar, it can be kept fixed if you want to see more or less how this dependence goes. But then you have 1, 2, and 3 three parameters. And so if you want to do the line that we were doing at the beginning, you have to have two projection, omega mater H and AS, and then keep one fixed each time and see what happens in this place. But you can play a different game the moment you go and look at the data, and then you can say, haha, but in F sigma 8, F of Z depends on omega mater, and actually in a lambda CDM, it goes like omega mater to the 0.55. And sigma 8 is actually a function, which I'm not going to write down explicitly, but we can, of omega mater H and the primordial amplitude. And I can rewrite this function in terms of M and the primordial amplitude. And therefore, now I don't have an under-constrained system. Now I have an over-constrained system. And you can do the MCMC as done before, but now picking different aspects of the model. And I don't want to go into too much detail, but what you will find out, in case you're interested, is that you end up with what Samuel calls scissor plot. That is, say in the amplitude versus H plot, you have one physical feature that constrain one degeneracy direction and the other physical feature that constrain another degeneracy direction. And when they cross, you constrain the parameter. So fixing, that's why you can sort of see that fixing the H tension and the sigma 8 tension in one go is different because you have this scissor plot. And so if you change one, you have to also change the other one. So you have to touch the model at different points and keep them coherent with each other. The same thing that we saw before with the M and the dV over RD plot. And so here's a summary of the H constraints by using different physical aspects of the models and the two target H0 camps, let's say. And some of you may ask, why is the orange high? And the aficionados will know why, and the not aficionados, I'll tell you the result. The orange is high because it's basically driven by a completely statistically viable high value of F sigma 8 from the high redshift beams. So from the quasar clustering. So it's just it's not even 2 sigma, so it's completely statistically acceptable. But then when you put it in the plot, then that's you see the orange going high, and then when you add the other data, this shift disappears. So this is not anything to worry about too much yet. So as a summary, it turns out that there is a lot of wiggle room. All these different H determination within a lambda CDM agree, even though they depend on different aspects of the model. So I think I should go towards my conclusion. And since I have another maybe 2 or 3 minutes, let me say the following. Since we already did a couple of trips down memory lane, let me do another trip down memory lane, which is asking, how old is the universe anyway? And does this help us testing different aspects of the model? And it turns out that yes, the look-back time and therefore the age of the universe depends again within our favorite model on the same quantity, H0, and the expansion history of the universe. And so one can do a plot like this, which we have H0 and the age of the universe, and the age of the universe, since depends on the expansion history of an H0, one can find the degeneracy direction that come from what we know about the expansion history, and then the CMB also gives us some constraint there. And then you can ask, well, can we measure the age of the universe at redshift 0? And then see where we land, because a lot of the age of the universe, because of lambda in a lambda CDM, it's a late time. So this is an integrated measurement of an age, not an age, but within the model you can connect the two, that will be heavily weighted towards the late universe. And so this was a big part of David Balsan PhD thesis, and looking at the age of the oldest globular clusters and redoing the analysis. This is a PhD thesis, which I'm summarizing in one slide, end up with an age determination that is there. And this led some of my collaborators to say lambda CDM acts is age, not its shoe size. So this is interesting because if we want to have this economy early versus late, this is something that is maybe a late kind of time measurement and late time physics, because age is weighted towards the late time. That is consistent with a value that is of age that is more in agreement with an early sort of value of age. But again, the error bars are not, they're still too large to say anything at the above the 3 sigma. So this is indicative, and there's more work to be done there. So let me try to finish. I think larger scales, I try to convince you that larger scale structure give you more than one age. And you have to be careful what you measure. Some quantity can give you only omega matter. It's the theory that makes the connection between what you measure and the parameters. And you can have an early universe calibrated H0 from late time observation via the BAO and a CMB or VBN inspired prior. But the large scale structure power spectrum can also be useful to give you information about matter radiation equality. So you can check self-consistency as a function of redshift, and another scale as a standard ruler at a different early time physics, and you have another over constraint system. And so the growth of structure give you F sigma 8 for more than one redshift, will give you omega matter. But then if you use the omega matter above, then AS and sigma 8 are related by omega matter and H and M. So again, you have another related system, and it tells you that you don't have a lot of wiggle room if you want to fix, if you assume there is a sigma 8 problem and you want to fix H and sigma 8 at the same time. So it looks like we are looking for Cinderella, but I hope I convince you that now we are doing that with more than a single slipper. And if you want to find out more, I leave you with the list of references. Thank you.
Thank you so much. Thank you for the very interesting talk. Do you have any questions? Yes, please, Shaheen.
Thank you, Licia, for the very nice talk. Actually, I have a couple of comments, if not questions. So in some of your earlier slides, you showed that if you take different data sets, you will get different values of H0. What happens, or one can actually take a single data set, for example, Pantheon Plus, or other data sets, and beam it into redshifts. So, and measure H0 at different redshifts. If we find that H0 evolves across the beams, this actually rules out the early resolutions to the Hubble tension. So, and the point is different redshifts versus different data sets. And the other comment is just theoretically, H0 is an integration constant. So, and if we find different values for this H0, depend if, for example, if we use different data sets or if we in the data, this means that the model is not working. So, of course, all these statements should be viewed within the error bars.
Mm-hmm. Okay. Yes, so if you look at Pantheon Plus cannot give you H0. Pantheon Plus can give you omega matter because it gives you the shape of this function history. If you assume that it is a lambda CDM, then you can extract a single parameter of this omega matter. If you don't assume it's lambda CDM and say you still want it to be flat, but then you allow the equation of state of dark energy to be different from -1, then you get a degeneracy between omega matter and W. So for the supernovae to give you H naught, they need to be calibrated. You need to know what the magnitude of the standard candle is, or standardizable candle is. But then to do that, you need to rely on the cosmic distance ladder. And then the cosmic distance ladder is true as different calibrators, and the best one is the Cepheids, and different calibrator gives you slightly different value of H naught, and then there is this whole study of whether there is more scatter within the calibrators than the error bar reported, and there's a lot of discussion there. But so it is true that the Pantheon plus omega matter is a little bit higher than, say, the Planck omega matter, but it's still consistent. It's still within 2 sigma, and we know that in one case out of 3, you are outside of the 1 sigma, which is totally possible. So that is not a problem. But yes, if you try to measure the same cosmological parameter with different data and you end up with different values, then you have to ask yourself, do I have a problem with the data, or do I have a problem with the model that connect those different observations to the same parameter, but maybe I'm not measuring the same parameter. I'm measuring actually different things. Definitely, yes, that's the important question to always have in mind.
Thank you so much. Leandros?
Yes, okay. Thank you, Licia, for a very nice talk. I have a question about the possible match between the calibrators. As you said, the essence of the tension is a mismatch between the 2 calibrators, the early time calibrators, sound horizon, K quality, with the late time calibrator, which is basically the absolute magnitude of supernovae. Now, most of your talk, essentially all of the talk, was focused on the possibility that the early time calibrators we should pay some attention to them. Can you comment on the possibility of there is something that we don't understand on the late time calibrator, on the absolute magnitude of supernovae, and which could be either due to systematics or due to some physics problem. Also, I want to point out as a comment that in fact Pantheon Plus, in contrast to Pantheon, can lead to measurement of H naught because it includes the distance moduli of supernovae which are in Cepheid hosts. So in that sense, there is some absolute distance data there. So in principle, one can get the H naught from Pantheon Plus because exactly of this distance moduli of Cepheid host supernovae.
Yes. So you want me to talk about something that I have not worked on, which is how do you calibrate the actual direct cosmic distance ladder? And I would say that my interest there is more, say, epistemological than actually technical. That is, these are very difficult measurement, and that then you interpret within a model. Where could you go wrong, and what are the type of tests you may need to do to convince the entire community that you cover all the possible corner and there's no wiggle room beside the error bar, so that there are not unknown unknowns. And again, talking about unknown unknowns, I find it is a little bit of a double-edged sword, because it's easy to sort of wave your hand and say unknown, but see, if we are in this business, we are in this business because we want to take the unknown, transform them in unknown known, quantify them, and propagate them into our error bars, maybe a statistical error bar plus a systematic error bars, and some collaboration are really starting to do that explicitly. And the TRGB latest papers by the Chicago Carnegie group actually do that and quantify. These are the statistical and these are the systematics. So my view there is that the data have been public for a while, and different groups have analyzed them and reanalyzed them. Some have retaken data with different instruments and different calibrations and all that sort of even instrument model and data model very close to the data rather than very close to the theory. And there doesn't seem to be a lot of wiggle room. Whether all the tests that have been done are exhaustive and there is no possibility that something else had gone wrong, I don't know. And I don't think like any single researcher can know. This is something that different collaborations with different expertise need to come to a consensus. So that's why I say the jury is still out in some sense. And my personal approach at this point is average everything and then keep a mind open, say maybe there is an issue, and if there is an issue, what are the consequences of this issue? But I wouldn't, yeah, thank goodness I don't have to bet.
Okay, thank you.
Thank you. Vivian?
Hello, Licia. Thank you very much for the nice talk. I wanted to come back on the last point that you brought up, the issues of the age of stars. I'd like to understand that a bit better.
Yes.
What is the prospects on getting this to higher accuracy? And if truth is correct and the median age of these stars stay the same, I mean, how hard would it be to get all the stars to be below, let's say, 13 gigayears? I mean, do we really what would it take essentially to, if truth is correct and the age of the universe is something like 13 gigayears? I mean, I'm saying shoes plus some sort of early universe change in the sound horizon, such that only at the end of the age of the universe in the end of the day end up being something like 13 gigayears. What would it take to make these measurements in agreement? Is it a complete contradiction, or do we have wiggle room in what we understand of stars?
Okay. So first of all, the high H naught that come from the direct distance ladder will want, in a lambda CDM with all the other parameters that where we seem to find agreement on,
yes,
a universe which is 13 gigayears or below, and then we know a Planck calibrated one 13.6 or something like that. So that difference is not much bigger than the current error bars. And then you go and look at the error bar and say, well, how can we shrink the current error bar from, say, the age of the older globular test? And so that error bar right now, it's basically half systematic, half statistical. And so in the Wiedewald thesis, there is this rundown of where the error comes from. So getting more globular clusters observations will not help. But getting better extinction, better distances from Gaia, that will help in some way. But then the rest of the uncertainty comes from the models, because you need to use this kind of model for an HR diagram for the globular clusters. And those models have intrinsic uncertainty. So you can't just take one model and say, I trust it. You have to use different model with different element abundances and all that, and then marginalize over this. And that's is part of the uncertainty, and that depends on the people that model those kind of things. It is not my expertise or any of my students to actually go into those details. So, but I hope that showing what the possible implications are and what the stakes are may actually motivate that community to put some work in that direction.
But
so it's not impossible, but it will require very specialized expertise of the people that build those models to actually sit down, compare, improve their modeling, and it's not a work of an afternoon.
Okay, thank you.
Thank you so much. Any other questions? No? So let's thank Licia again. Thank you so much.